Welcome everyone to today's robust optimization webinar. So it's the kickoff of the fifth season of RO, and it's my great pleasure to introduce Peyman Mohajerin Esfahani. So Peyman is actually known for his seminal work on this data-driven distribution and robust optimization that actually revolutionized the distribution and robust optimization domain. So Peyman got his PhD from ETH Zurich, Switzerland, and then had several research appointments at EPFL, ETH Zurich, and MIT. And from October 2016, he joined Delft University of Technology in the Netherlands, where he is now an associate professor. He is also an associate editor of several prestigious journals such as Mathematical Programming, Operation Research, Transactional and Automatic Control, and Open Journal Mathematical Optimization. He has received many awards, so the list is long to just mention all of them here, but to name few of them, he received the ERC Starting Grant and the Informs Frederick Lanchester Prize in 2020. So it's an honor to have you here, Peyman. And without further ado, I want to give the control of the mic and the screen to you.
Thanks a lot, Ahmad, as well, and also Yanis for invitation, and thank you very much for a kind introduction. So it's a great pleasure to kick off this year webinar. So what I'm going to talk today, and by the way, feel free to interrupt me if there's any question. I could not see people actively, so you just simply unmute your microphone and talk if you want. So my main topic that I decided to talk about today is about inverse optimization. But the main motivation that actually somehow captivated me in the last couple of years, and I got interested in the topic, is that one of the topics that has a close connection to convexity in general as a property, and how this convexity comes handy in several aspects of learning. And this is something that I found it particularly useful in inverse optimization topic. And soon I'm gonna comment on that, how I see it and why I think such kind of property can show up here. So with this very brief discussion, so okay, now it's working. Okay, so basically my talk has three parts. So the first part, I'm gonna talk about very general framework of data-driven decision-making, and particularly in relation to the subtitle of my talk in terms of role of convexity in learning. And then I move on to the main part of my talk, which is related to the inverse optimization. And then I want to motivate the whole conversation that I had, at least to my best experience, through several applications that I had in the last 3-4 years. So let me start from what is data-driven decision-making in my mind. And when I go through each topic, I basically have one takeaway message in my mind that I would like to communicate upfront, that basically what would be a takeaway message, and if you got that one, I would be more than happy, is that basically I want to pose 3 different research questions and how convexity plays a very useful role in that. So let's see what are those questions and what is the data-driven decision-making. So the first, so let me start from a very basic setup of data-driven decision-making. So basically, any decision-making has 3 fundamental ingredients. You have a decision, you have an uncertainty, which you usually don't have it at the time of decision-making. And then there is a loss function, which basically takes these 2 values and delivers some number in R. And this loss function is what you perceive as the performance of your decision. Now, when we talk about data-driven decision-making, you can think about it as 2 processes. The first process is that we collect some data from this uncertainty, and I want to annotate it by past, because this is usually what has happened in past. Based on these decisions, based on this data, you make a decision, and that's the first arrow here, and this is the decision that you make at the present. But when we talk about performance, what we typically care about, both theoretically and also practically, is not the performance of this decision on the past data, but rather on an unseen data that may happen tomorrow. And this is what I put it as a future, and this is more about the second arrow that I mentioned here. So this is very abstract, but let me just conceptualize it through a very basic but important example. So think about the basic curve fitting problem. So you have a bunch of points and you want to fit a hyperplane to these data points. And when you talk about data, basically these are these two-dimensional data that you have, and you want to fit, let's say, a hyperplane through it. So the decision that you want to make is this simple hyperplane, however you parameterize it. So this is the decision that you want to make based on these data points that you have. Now, when you talk about loss, when you look at this, clearly these are the mismatch of your curve fitting to the data that you have, and you can see these are exactly these loss function evaluated on the past data. But now when we talk about performance in the future, what we really mean is that what would happen if now I draw another sample, and now I want to talk about the fitness of this curve fitting on the data that we haven't seen. So this is basically a very simple example that I hope to capture all these two phases and the important aspects of that. This is a very old and classical problem, and many communities, including operations research, machine learning, and even other like statistics have looked into it for probably more than half a century. These kind of problems got different names, and I just want to take a moment to just share the names that I have come across. So if you go to the machine learning literature, you can see that this first arrow, they usually call it training. The second arrow, they usually call it test. So you want to test the performance here. You want to train what you have. And the difference between the future loss and the past loss, they sometimes refer to it as a generalization error. And all of these words have a very conceivable meaning to that. So you want to generalize from the past loss to the future loss. When I started working with operations research community, which probably more of this audience, I came to realization that are a little bit more creative with names. So what I learned is that the first arrow, they usually refer to it as a prescriptive analytics. The same problem, the same thing, but they refer to it as a prescriptive analytics. The second arrow, they call it predictive analytics. And perhaps the most creative one is the difference between future and past loss, and they sometimes refer to it as a post-decision disappointment. So the difference between what you expect to see in the past and what you will see in the future is sometimes referred to as post-decision disappointment. This is basically at the conceptual level, but if you want to formalize this conversation and exactly say, what do you mean by this loss, there are more complication to that. You need to take into consideration that this is a random variable with two different sources of uncertainty, both the uncertainty about the data set that you have, as well as the data set, the sample that you will see in the future. So the conversation about these post-decision disappointment usually is a formally complicated one. So now in this picture, if you hopefully clear what I said so far, now we can actually go back to those three research questions that I was hoping to cover here. The first question is usually about the first arrow, the trading phase, the prescriptive analytics phase. And this is usually where the focus is on the computational side, and people coming from optimization background with optimization algorithms look into these kind of challenges here. So how to turn this data to a decision in a more computationally efficient manner. The other question is what I was just talking about, more about this post-decision disappointment and predictive part of the analytics, which more is on the statistical side. There is also a third question, which maybe in the last 10, 15 years got renewed attention, is I would like to comment on that like a real-time evaluation, a real-time aspect. And what do I mean by real-time aspect? What I mean is that imagine that you already made a decision, which is this theta hat n and hyperplane. Now you get a new data point. And now the question is, what would be an updated version of the decision that you get? So how would you in real time update this decision? A trivial answer is that, yes, I can put this one into this past data and redo this arrow here. But the question in the third part is something more intelligent, more efficient, instead of redoing everything from scratch. And if I put it a little bit in more mathematical formalism, what exactly mean is that can I actually estimate the new hyperplane instead of computing this theta hat with n+1 only by an algorithm that takes value current decision and just the new data point. So this kind of approximation, it pops up in online optimization literature in real time. And those people coming from control background know that, for instance, it was one of the central property of, for instance, Kalman filter, for which we have such kind of exact reformulation for a very special class of problems. So here what all I'm trying to point out are three different research questions with three different focus. And what is, in my opinion, quite interesting is that if you happen to have a convex property here in the decision variable, you actually have a lot of tools and properties that you can enjoy at all these three levels. It is kind of, we all believe that the convexity is one of the best property on the computational side. So this is a kind of trivial thing to say, but it's much less trivial when you know that even convexity can help on the statistical side, but also on the real-time evaluation. So these are basically what I gathered in the last 5-6 years. When I look into the literature, I see how convexity could be useful. And that was kind of the motivation and somehow feel the need that I had to, if possible, to turn the learning problem into a convex optimization by some means. And this basically brings me into the main topic of today, which is inverse optimization. So what is inverse optimization? I'm going to introduce a particular framework of class of problems in supervised learning. And inverse optimization is a framework that would help to preserve this kind of convexity while it has a rich property and also interpretability that would be very handy for learning models. So if you didn't follow some details here, that's perfectly fine. All I said is that if I end up with a convex optimization during learning, I can benefit in three different levels. And how we can translate a problem to a convex optimization while we have some limitation at the modeling level, that's the conversation that I'm going to proceed with that in this part. Okay, so let's see what is inverse optimization. But before going to the inverse optimization, I just want to comment on supervised learning as arguably the most general class of problems in machine learning that find many applications. What is supervised learning is basically function approximation. At least as far as I'm concerned, I see supervised learning as a function approximation. So we have some, I call it black box. You can think about it like a function that from some input, here I denoted by S, and then output on X, and I want to approximate this function. So the example that I gave earlier about curve fitting is one of the problems. It's basically the same thing. So the curve fitting, let's say the x-axis is S, somehow bad notation in terms that usually we have x, y here, but let's agree that this is S and this is X variable. Soon you will see why I chose the output X in the context of optimization. And basically, imagine that the black box is a hyperplane that you want to learn it. That's basically what we are going to do. And when we talk about supervised learning, we try to learn the slope of this function, and that's basically how the approximation looks like. And this is where the parameter of learning pops up. This is perhaps the most classical one in supervised learning, which we call it linear regression. So we parameterize the parameter and try to estimate the output with these parameters. And this is a class of parameterization that you can easily end up with a convex optimization, and then you do what you wanted to do. And it has numerous applications. What I want to focus now in this talk is two challenges, two particular difficulties that challenge this linear parameterization. The first one is when instead of such a nice function, such ground truth function that you try to estimate, you have discontinuity. So if it so happens that you have some discontinuous behavior from this input to this output, then such kind of parameterization is going to be very difficult to capture this behavior. If you know exactly where the discontinuity happens, that's okay. You can actually, instead of going with this kind of polynomial basis, you can go with a more complicated basis like phi 1s to phi ks and parameterize it like that and try to capture this kind of weird behavior, some abrupt changes. But you can only do if you know exactly where this happens. In other words, you need to put a lot of basis function with different discontinuity so that one of them happen to be close to the ground truth and capture it. Maybe if you look at in one dimension, that's not a big deal. In one dimension, I put enough number of basis function around it so that we can have enough exploration and find it. But when you go to the higher dimension, and what do I mean by higher dimension? When the input space increases, something like multi-dimension, so you have output and multiple input, then you can immediately start seeing that finding where exactly this discontinuity happen is basically the entire problem. So you really need to, not only to put here, you put all the other different points so that the data that you have hopefully give you enough information to capture that discontinuity. So long story short, what I want to say is if you have some abrupt changes in the learning function, you sometimes need exponentially many basis function and exponential in the dimension of the input so that you can immediately capture it if you go with linear regression. So that was kind of, and remember, it's not one. You can imagine that the function you want to learn has multiple discontinuity behavior. So that would be one of the challenges, one of the main difficulties that challenge the linear regression, the classical linear regression. The other challenge is when you have multivariate output. So the X variable is also not one, it's multivariate output, and they are correlated. They are related to one another. You cannot think about this curve fitting like multiple univariate regression. These outputs are correlated. For instance, in this example that I'm showing here, you have 4 outputs, and let's say summation of all of them has to be smaller than 1. You cannot have more than that. Just, I guess here it's more, smaller than 2, I guess, in this example. So when you want to learn, when you want to fit this parameter from this input to all 4, there are some correlation that is important. And if you just go with multiple univariate linear regression, you would usually lose that kind of information. So these are 2 challenges that in many applications also become very important when depending on the application, but it can happen. And I'm going to comment on that where, for instance, this is the case. And this is basically kind of the starting point of this inverse optimization class, at least as far as I'm concerned, that could address these 2 kind of challenges. So now with this short introduction, let me go back to how we set up a basic of supervised learning. So if you want to solve a supervised learning, you basically need 2 main ingredients. The first ingredient is that you need a hypothesis class. You parameterize a function. I just put it number 1. This you parameterize this, and then now you want to find the best parameter within the class that you have. For that, you need another element, which the second ingredient that you need, I call it loss function. What is the purpose of loss function? It's basically, it's a kind of similarity measure between the real output that you measure with predicted output that your function has. So you want to make sure that these are close to one another. So if you look at, for instance, linear regression, the best, I mean, not best, sorry, the popular L function is norm 2, and that's how you compare how the output, the real data is far from the predicted one. And if h theta is linearly parameterized here in theta, that's going to be a simple quadratic function. So that's the one of the popular one. And once you have, this is just an example I gave it. And then once you have these 2, speaking of the training phase or that prescriptive phase, that's a kind of optimization problem that we solve at the basic level, that we actually collected the data and then we minimize the empirical loss over the all data that you have. Remember, the data that you have now is the pair of input and output, and the pair is going to be the psi variable that we had as a data, and then we solve this optimization problem. So this is the very basic supervised learning setting that we have. And I hope by now I managed to convince you that if you have some difficulties like what I mentioned, like multivariate output and discontinuity behavior, linear regression may face difficulty to serve the purpose. Now that's perhaps the first time that I want to introduce now what is inverse optimization. In my mind, inverse optimization in the context of supervised learning is just a particular class of H theta. So this hypothesis class now, H theta, as a hypothesis class, is you can think about it like a parameterized optimization, parametric optimization. So in other words, the function that you use itself is an optimizer. And the parameter usually, at least historically, first appears in the objective function. So you try to learn the objective function of this parametric optimization. I deliberately changed the color, the input to S, so that you can easily track where the S variable as the input enters into the consideration, into this optimization. It could influence the uncertainty set, but it could also, the output set, and then also it could influence the objective function. This is a most general setting that you can imagine. And as long as you have this class, this is how I see as an inverse optimization. And it's called inverse optimization for probably this reason that in optimization, you usually have the objective function and you look for the optimizer. Here is the other way around. Speaking of data, you have the output, which is the optimizer, and you want to inspect or to learn the objective function. That's the reason that it got the name of inverse optimization. Now, think about this hypothesis class. Now I want to say few important things in relation to this hypothesis class. First, whether this is a meaningful class in application that you have. What I found it actually when I started working on that, what I found it actually most of the problems that at least I face, the application domain is more of this kind of setting than just a simple function. For instance, if you look at all biological systems, when you collect the data and you look at the nature, how it behaves, what is very interesting is that more often than not, we believe, or at least biologists believe, that nature optimizes something. What we don't know what is optimizing, but we get to see the decision of the nature. So it's actually fall very naturally into this category of hypothesis class that you get to see the decision of the nature. This black box is the nature, but you don't know what is optimizing. And that's going to be the interpretation of this F theta that you try to learn. When it comes down to the human decision making, that's even more conceivable. Think about consumer behavior. What happens in consumer behavior, you see how much they buy, how much they sell, or how they behave. You don't know how they end up with this decision, but you see the decision. So this is also another huge line of application that if you want to learn it, it naturally falls into this category as well. And speaking of this signal, by the way, we chose S input because actually it came from this consumer behavior application, at least to the best of my memory, is that they call it signal. And the signal that they send to the consumer is basically prices. So these prices changes, and then the consumer make a decision how much buy or not to buy. And by the way, speaking of discontinuous behavior, we can all see that we kind of behave as a human decision maker like a discontinuous behavior. Up to a certain price, we buy it, but then suddenly we stop buying. So it's a kind of very sharp transition from what we do and what we not to do. So this kind, if you want to learn that one, that's naturally some sharp transition that you want to learn how it happens. The last example that I want to just point it out is market behavior. So in all market, what you get to see from market participants is the bid that they put in the market. But you don't know, and actually it's quite sensitive information, that how the participant end up with this bid. So now I know that I'm raising a little bit sensitive subject, but that's actually an interesting point that if you really have data and you use this kind of behavior, you can infer the decision-making mechanism behind these beads.
I have a
So
question,
sure,
Peyman.
sure.
So in general, when we see inverse optimization problems, generally it's posed as a parameter optimization problem. But when I
It
see
is.
here, you write H theta S, it makes me see that this is a policy optimization problem. So,
For me,
right?
both of them are the same. So when you say parametric optimization, I
Yeah.
100% agree. This guy is a optimization problem and parametric in S.
Okay.
So
Okay.
that in the language of parametric optimization, parameter is S.
Okay. Okay.
Okay. And when you talk about policy, if you mention something in the context of, for instance, reinforcement learning,
Yeah.
that's like a Q function. This is the Q function, and S is
Okay.
the state of the system. And so for me, policy and this inverse optimization, they're one-to-one correspondence.
Okay. Thanks.
So basically, in this slide, all I try to say is that this hypothesis class in certain application is actually very naturally interpretable. And F theta by itself has an interpretation for us. And that's the first thing that I want to say. The second thing I just want to very briefly point out that how this F theta looks like. For all the applications I'm going to show today and the results, I'm going to go with the linear parameterization. Actually, being linear is the key feature for us. So when I say linear, I mean parameter in theta is linear. Linear appears here. I just go with a quadratic form. And these are the parameters of the cost function that we try to learn. And this is output information. So if you have a multivariate output for which you have certain information, then you can encode that one into the constraint here. So that's actually another point I mentioned earlier, that you have two challenges about multivariate output and certain condition that you have. Naturally, you just put the constraint here and then you go with that. And if I want to, this is a very rich class. And just to give you an example is that linear regression is a very particular case of that. And where it is a particular case of that is when you don't have any constraint. So if you don't have any constraint and you have just this quadratic optimization, you can just do a basic derivative, set it to 0. And then you see that actually the relationship between the output and the input is going to be just a linear relationship. And here I put it as for simplicity, but you can imagine that I can have something like phi of S, and I put phi of S here like a basis function in the linear regression, and I end up with the same philosophy, and I get the same thing. So linear regression is a particular case of inverse optimization when you don't have any constraint into consideration. Now, I guess the most important thing that I want to say today about inverse optimization is in relation to this constraint. So you remember that I told you that one of the challenges, and in fact, the main motivation of inverse optimization is that you may have discontinuous behavior from this input to this output. And if you want to capture that in linear regression, you need exponentially many basis function with discontinuous behavior and exponential in the dimension of S. What is very interesting, and in my opinion, most important feature of what I'm talking today, is that from a convex analysis, from an optimization point of analysis, you can show that this H of theta, the optimizer, can exhibit discontinuous behavior at the extreme point, at the edges of the polytope. And we all know that polytope has a very magical property. The magic is that while you have polynomial representation, you really have an exponentially complex object in terms of vertices. So while you have just simply something like Cx smaller than D, and C and D are just polynomial size matrices, you really parameterize exponentially many vertices. And these are the places that these hypotheses can actually have discontinuous behavior. So in other words, if I manage to learn this theta efficiently, it's essentially benefiting an exponentially many basis function there while I'm dealing with polynomially many parameters. And in my opinion, to this day, the best understanding that I have for some positive result that I got is, in my opinion, coming from that the model is rich enough with a lot of potential discontinuous behavior. And if the ground truth has some discontinuity somewhere, it can capture it much faster with much lower number of parameters comparing to, for instance, neural network or linear regression. And I'm going to show an example of that today. So that's the last point. And I think from a, let's say, research point of view, the most important thing, okay, I show you a very, let's say, rich class, and it can capture discontinuous behavior, even exponentially many discontinuous behavior in the space of S. But the question is, can I learn theta efficiently? And that's, from a research point of view, perhaps the second main message of my talk today. Now, let me communicate this through some geometric interpretation. Let's go with the least square loss function, arguably the most popular one. I put this loss function with denoted by P because sometimes in the literature they refer to it as a predictability loss. So this predictability loss is basically the distance between the true data and what you predict. So if I want to visualize where this guy is, let's look at this behavior. So imagine that this f theta is this objective function. The horizontal plane here is where the output lives, the x variable lives. So this is the data that you have seen. This is your hypothesis objective function. And S is just an input variable that may influence this objective. Now, if you look at where the optimizer is, the optimizer is here. This is the optimizer of the objective function that you try to learn. And speaking of LP, this is this distance. So the LP is the distance between X and H. Just to remind ourselves, when you do learning, you change the theta parameters. So you change this cost function and this loss function changes. Of course, if the loss function is, first of all, a loss function is always positive, and it is zero if and only if the predicted output is exactly the data that you have. So it serves the purpose that you expected, and this loss. But I already hopefully convinced you that H theta can be discontinuous in terms of S. So if this guy is discontinuous, if I change the theta, you can imagine that this could be even non-convex and can behave widely. So this guy could be non-convex. Now the main question is, do I have an alternative to this non-convex loss? And the one that I want to introduce as a replacement is something that we refer to it as a suboptimality loss. It's a little bit, it's hard to parse it here, but let me tell you what I call it suboptimality. First of all, instead of reading that, maybe that's the best geometric interpretation. So this distance is the suboptimality of the data, the real data in your model. So this f theta is your model. This is the optimizer of your model, but this is the true data. So this loss function is the suboptimality of the true data in your objective function. This loss function mathematically is described like that. So it's going to be the f theta sx minus the objective function evaluated at its optimizer. And what is interesting is that this is actually convex in theta when f theta is linearly parameterizing theta. And that's the only proof I have to show you today, because it's just 2 lines. It's very basic. And the basic point is that if you look at this quantity, by definition, this is the optimizer of theta. So I just simply replace it by minimization. And then I just bring it out, and it's going to be max of this quantity, which is linear in theta. And max of linear functions, we know that it's the convex function. So at the very general level, this loss function is a convex loss, whereas the other one is not. And that's a good alternative. There are relationship between these two, but the relation, and by the way, again, this also coincides. This is always positive, and it is zero if and only if this guy, the output, is the optimizer. Oh, sorry, the output, the real output, is the optimizer of the objective function that you have. Okay. So now I'm having an eye on time. So maybe I very briefly also touch on another point, is that the relationship between these two guys. So imagine that the data that you get, also the ground truth here falls into the same category, the same hypothesis class that you have. So what I mean by that, so imagine that there is a theta star that generates the data that you have. And in this case, you can imagine that this is the ground truth that you're looking for. And ideally, you want to hope that theta coincides with theta star in during the training. And if this is the case, and if this f theta is a convex function in y variable, under this regularity condition, you can show that actually the LS is there's a dominant relationship between the suboptimality loss and predictability loss in the theta parameter, regardless of the data point that you have. And this relationship is interesting in one point, is that if the ground truth is theta star, both of them achieve the theta star 0. But what is interesting is that one could be non-convex, whereas the other one is convex. And that basically means that if you apply, for instance, gradient descent to this one, it converges to the global optimizer, whereas the other one does. So this is pretty much the main message about the loss function when you want to use inverse optimization for modeling. Now, I just also want to take 1 minute to cover at least my best knowledge about the history about this loss function in the literature in the last 5-6 years or even more. So these two loss functions that I just presented here, the predictability loss was studied by Anil Esfahani and was published in OR 2018. And Anil looked into various aspects of the predictability loss, particularly with some emphasis on the statistical side, consistency, and so on. And then we look at the suboptimality loss around the same time, and it was this one. But when we go to the particular choice of the class where these are convex optimization. So what I presented here, these two, everything that I presented, you don't require any condition. This set could be non-convex. This optimization problem could be non-convex, and still this loss function works. But if f theta happen to be convex in y, and y here, this is also convex set, then there are multiple other options. And these are the 3 options that I can collect from the literature. Maybe one of the very first one was this KKT loss. This is a loss function that comes from the duality. They use some duality, and it dates back to 2011. But also Bert Simas and his co-authors also did some work in a more general setting, not just inverse optimization, but also some Nash equilibrium or some multiplayer equilibrium point with first order lies. These two loss functions, these are different. There are some relationship to this, but they are not the same, but only meaningful when the hypothesis class is a convex optimization. And then in the particular case, so these two are convex optimization. If you go to the linear inverse optimization, so the f theta is linear and this is polytope, Timothy Chan and also his co-authors look into the some geometric property of the particular case of linear inverse optimization that was published in Management Science. Interestingly, all around the same 2018, but in different settings with different messages. Now, personally found it not long time ago, maybe even in the less than a year ago, is that there was also another work which had this title of Smart Predict Then Optimize. I don't know if you came across it, but basically the main message is that if I have to predict a variable that later I use it in an optimization problem, Should I first predict the parameter, then use it? Or no, I just try to learn the whole scheme together, and it revolves around it. El Maktoub and Grikos from Berkeley actually looked into it. The context does not look like that it has connection to the inverse optimization. And but actually, I have to say, during the review process of our recent work, the reviewer came to and brought to our attention, and I found it very interesting, is that the loss function introduced here is a new one comparing to these two, and that actually is this loss function. So there is a third picture one, which is in parallel to the to suboptimality, but now suboptimality of your predicted loss, your predicted response in the ground truth loss. So now this quantity, this is a third one, this is a different one. This is also could be non-convex, discontinuous, and they actually propose some convexification in the same fashion of 0-1 loss in support vector machine. But it was interesting that I thought I personally like it, so I just want to present it, that it has some connection to that. And if you think about this, and you want to this predict and then optimize, is exactly referred to this theta star. So you don't know theta star, but when you find theta star, you want to put it here and predict this guy. That's the context of that. So this context of this paper also very close to inverse optimization, at least the way that I see. And maybe just last word from our side is that so very recently also we look at some of our students and the recent work that we have done, that we actually look into, instead of finitely many parameters, which is the context that I presented it, we extend it to some non-parametric learning, particularly using kernel method, in which we do not have finitely many parameters. We have actually infinitely many parameters, so to speak, and this phi belongs to a certain class of reproducing kernel Hilbert spaces. Then we learn it from there. But basically, all the theory of representative theorem and directly applies, and we can use it with suboptimality loss, and it works. So now I look at the time, I see that I have about, let's say, 5-6 minutes. I have more material than that. I'm thinking whether I should, because I have one topic related to the robustness in the spirit of the webinar talk, but I also have a few applications. What should I do, Ahmed? Should I move to applications and present it?
Fully up to you.
Okay, so
you're the boss.
Thank you. So I covered 1 minute about robustness, just one particular robustness. I know that I'm gonna go fast a little bit, but if you have any question, I would be happy to take it after the seminar. One thing, when it comes down to the robustness, which is the spirit of this seminar, what we mean is that we have a usual optimization problem, and then we want to put some robustification, some min-max problem, so that we robustify with respect to whatever uncertainty is there. So this is also actually in the 2008 paper, we also looked into some sort of distribution robust version and apply some theory there. What we had done recently is that we tried to give some tailored robustness with some interpretation to the loss function of inverse optimization, and that was the focus. What it came to our attention, and I think it's a very special and inherent property of this loss function that I introduced, is that if you zoom in around the optimizer, inherently the inverse optimization class during learning has multiple solutions. You can think about, remember, this theta appears in the objective function. So imagine if I multiply theta with 10, all parameters, if I scale it with 10, the optimizer doesn't change. If the coefficient are positive, the optimizer of the objective function doesn't change. So there are directions in which if I change, the loss function does not change. So in other words, this loss function in a way is homogeneous. In certain direction is constant. So in other words, more often than not, and inherently, you have multiple solutions for this class of problems. And when you run optimization problems start from outside and converge to one of the points here. Now the question of robustness is that now that I have multiple solutions, inherently, which one should I choose? And there are multiple ways to think about it. And two very famous concepts generally in the literature was, one of them was circumcenter and the other in-center. What was circumcenter? You say, look, I find the center of the smallest bar that contain my polytope. That's a kind of good center. So if I do optimization, I want to select this one. And you have some game theoretic interpretation to that. Like you can think about nature as adversary that want to pick up theta somewhere here, and then you want to have the minimum distance to that. The other one, and by the way, this is NP hard problem. So even though they looks very similar, this is provably NP hard. The other concept is when you put the biggest circuit inside the polytope. And this is the kind of robustness with respect to the edges of this polytope. So if the edges changes, you want to still remain inside the polytope. What would be the safest point? These 2 points could be far from each other. They are different concepts. And interestingly, one is tractable and the other intractable. And this is also what we looked into it in the context of suboptimality law. And what is rather not, so what I would say from a technical standpoint could be a difficulty is that these things are not happening on the normal hyperplane. These are happening on the sphere because, as I mentioned to you, this is a particular loss that is homogeneous. So you need some consideration on that, but still the message remains the same. So I didn't cover much detail, but I just want to say there are some robustification to some tailored robustification to this kind of loss that I would be happy to cover it later. Now, this brings me to the last part. So the next 5 minutes, I hope to just hopefully convince you with some application as well. And if I would have, in the spirit of my talk, one takeaway message, what I'm hoping for to have some competition in our literature for these very growing and powerful neural network models, but with some advantages that we might have. And I want to just comment on that. So for that, I pick up 3 applications. The first one is coming from the background that I'm coming from, the control background. And that's related to the model predictive control. If you don't know what model predictive control is, you don't worry about it. Basically, it's a real-time optimization problem. And in that way, for those that know what the model predictive control is, model predictive control look into the, let's say, 10-step horizon and then make a decision and go to the next step and keep repeating this receding horizon fashion. And in that sense, inverse optimization is model predictive control with the horizon 1, because I just compute, I have one cost function, not multiple cost functions running costs. In that sense, you can also compare it with MPC. So what we did in this experiment, I pick up this is the lab helicopter model. This is an experimental setup that we have in our laboratory. And this is the MPC that was implemented here to control this helicopter. We replace it with inverse optimization and we try to estimate it. From a theoretical point of view, we know that MPC cost function is exponentially many quadratic pieces in the horizon that you look into. So this approximation, you can think about it as one quadratic function that try to estimate max of exponentially many quadratic functions. So what is happening here is a max of exponentially many quadratic function, and what is here is just one quadratic. So we just try to approximate that. The number of parameters that we have was 36. And this is just the experimental results. So these are not simulations. These are implemented in practice. You don't need to worry about what is happening here. Maybe just the first window I wanted to show you that what is happening here and what is this axis is the difference between this prediction from MPC. So MPC makes certain decision, and then we look at how inverse optimization makes a decision and look at the difference. And this is the number of iterations. So each second, we collect one data from MPC and try to learn it. What is, in my opinion, very interesting is difference between these two. And if you just want to give you what is the difference, this is the difference between two different loss functions. One loss function is suboptimality loss that I just presented. The other one is spiritually very close to the predictive and optimal. So the loss function that predict the whole data and then the theta and then use it. What is not surprising, and by the way, this guy corresponds to the least square. And this is, you can think about it, this least square on these data points. What is interesting is that since I have 36 parameters unknown, it's very natural, and this is also a very typical behavior of least squares, is that around 35, 36 is exactly when suddenly the estimation becomes very good. So at the beginning, you don't gain anything, and suddenly when you have enough number of data corresponding to the unknown parameters, you suddenly learn the Q function, and then it does a decent job. What is interesting is that this suboptimality loss does not bother to learn theta exactly. Directly try to learn the optimizer. To learn the optimizer, you don't need to learn the old Q function. You may just need to the part of the Q that generates the decision. So within, I think this is 7. So with 7 data points, it does the job that the least square has to do it after 45, 46 data points. So the number of data points reduces by a huge factor. So that was the interesting experience that we had with MPC. Then we go to another application. It's more on the robotic, but basically the same control problem for those people that have experience with robotic applications. They have, let's say, state-of-the-art open source environment. They call it Muyuko environment. And it has numerous cases in this environment, which shows this walker, the two-dimensional walker. This dynamical system is way more complicated than the helicopter. The helicopter has about 7 states or 6 states, I don't remember. But this Muyuko has 17 states, which is quite high for a control problem. The state of the art here is a neural network. And if I want to give you what is the size of the neural network there, this is maybe the most interesting part for me personally. The neural network that controls this walker has 2.5 million parameters. And for learning 2.5 million parameters, it requires 1 million data sets. And it scores the highest to the best of our knowledge there, which is this. What we did here is that we just put the neural network here. We collect the data and try to learn the inverse optimization with only 840 parameters. In all fairness, we also did a little bit feature engineering for the relationship with S. We put some sinusoidal because we see that the behavior is, the behavior is a kind of, anyway, it doesn't work now anymore. So the behavior is kind of periodic. So we have put some periodic signatures there. And with only 5K training, it reaches to the decent level that can actually control. And what this one that I showed you was the implementation of inverse optimization. Before I go to the last example that I want to show today, one thing which is very important that I have to point out is that what this neural network does, and we did not do here, is solve a reinforcement learning problem. So when they train this guy, they train it so that for the Bellman error minimizes. So they minimize the Bellman error to train this. What we did here was not a reinforcement learning. We did supervised learning, as I presented here. So we kind of cheat in the sense of this comparison is that we look at the neural network, replicate the neural network. Whereas when neural network was trained, it was trained to solve a reinforcement learning problem. So we mimic it, but it still doesn't change the message. It says that you don't need 2.5 million parameters to exhibit this behavior. Maybe some much lower parameter helps. And particularly in view of much lower data point comparing 1 million, it could be very important. And that's the last application that I want to show. And I keep the best one for this audience last. And that's this so-called Amazon challenge, the last mile Amazon challenge. This is a classical vehicle routing problem. It was initiated by Amazon. What is about? Basically, in one sentence, Amazon is interested to know how the drivers make a decision to drive the trucks in the city. Why was the case? Because when Amazon instructed drivers to go through a city given the demands and customers' time windows that it has, it realizes that usually truck drivers do not listen to what exactly say. They do something else, and they actually outperform what Amazon people taught and instructed them. So in other words, they are convinced that the truck drivers know much better the city than those people sitting in the office in Amazon. No surprise, but what was interesting is that how they make a decision, how they actually evaluate the current status of the city, the roads, and how they can make actually such kind of decision. So what they did, they actually introduced this Amazon challenge. They put about 6,100 real-world routers from these human drivers, and then says, okay, replicate the behavior. Tell me a model that I actually give this input, demand, and customers, and then I can actually find exactly the route that the drivers take. And if you think about it, we are talking about a scale of city. If I'm not mistaken, I'm not sure, this might be New York. We are talking about a very huge city with many routes, and 6,000 is not much to learn this kind of complex behavior. So speaking of scarce data, is a very relevant challenge in this application. And for Amazon, that was a very important problem. And if you're not convinced that, and you have any doubt about that, maybe the price of this challenge convinced you that it was very important for them. So it was 175K, the price of this challenge. And what happened is that, by the way, we were not in time to participate properly in the challenge directly, but what we had a chance is that we used the data. And we using the data, we managed to implement this inverse optimization. And what you can now interpret to inverse optimization is the behavior of this theta. And this is exactly the driver's preference. And this theta for each road in the city, we have a parameter and we actually can measure it. And that's what you can perceive it as the driver's preference. So that was basically the final result that I just showed you in one shot. But basically everything that we said in terms of training goes similarly to this talk. And in terms of, we managed with a lot of effort to reach here, the second one, but we never managed to beat the first one. And the mastermind behind it was Pedro Zattoni. He graduated by the time, so I think this project for the time being this is the best we could get on inverse optimization. Whether we get here or not, I don't know. But that's pretty much my talk. I guess I exceeded much than you probably expect, but these are all the papers that I was talking about, and I would be happy to take your questions.